say that about 1 hour ago I found out that I have to give a talk this morning, so I will do my best. But if I am missing something, I hope I can answer your questions at the end of this talk. So I am a PhD student at the Kent State University, and this is the building where I am working. And what I am doing is just basically control over particles in liquid crystal. So the talk of today will be the experimental observations of nonlinear electrokinetic flows around a sphere in isotropic and nematic fluids. So everyone knows electrophoresis is a quite simple phenomena. You put a charged particle in a fluid, apply an electric field, and the particle moves linearly with the electric field, and also in the same direction as the electric field. However, if you put the very same particle in a liquid crystal, the phenomena is completely different. And in the case of liquid crystal, the velocity will go as the square of the field, and the directionality can be completely different to that of the field. So this is a very brief summary of our previous results. You put a particle in a liquid crystal, it forms some defects around the particle, and when you apply the electric field, the particle polarizes, and the particle moves with an even with that odd power of the electric field in the same direction. But remarkably, we can see a motion that is perpendicular to the direction of the electric field, and not only in a different direction, but also goes as the square of the field. So if you look at the theory, there is nothing that will tell you that the particle should move in a direction that is perpendicular to the field. So this is rather unusual. So we want to answer this question: what is the driving mechanism responsible for this particle to move in a completely different direction of the electric field? So here there are some. There's a summary of the possible mechanism that could happen when we have a particle in the liquid crystal. The one is the first one would be the dielectric reorientation of molecules, because they are susceptible to the electric field. So they can create a backflow close to the hedgehog. The second is that because we have a large splay near the hedgehog, we can have a couple flexoelectricity that could break the symmetry. There is always ions in the fluid, so we also have to consider the ionic flows. It could be that all of the above and also none of the above, so we could be completely wrong. But you can see that working with the liquid crystal is more complicated than just regular isotropic fluids. So to simplify the things, we need to choose a mixture with low dielectric anisotropy. So that means that we want to minimize delta epsilon so that there is no reorientation of the molecules around the particle. So in this case, we can neglect the effects of dielectric reorientation and also the coupled flexoelectricity. So that leaves us only with ionic flows in principle. So if we are interested in the ionic flows, then we need to visualize them somehow. So we are using micro PIV. This is particle image velocimetry. So what we do is just put some fluorescent tracers dispersed on the fluid and see what kind of patterns we can get. So this is the main experiment. We put particles in a well-aligned liquid crystal. Particles will create defects around it. In this case, we have a symmetric or quadrupolar type of pattern. This is so-called Saturn ring. And in the second case, we have a point defect. And in this case, we have a broken symmetry of the pattern. So what we do is just put the tracers or the fluorescent seeds dispersed on the fluid and apply the electric field and see what happens. And what we saw is that the tracers start moving with the field and start describing these kind of patterns around the particles. And you can see that for symmetric particle, the patterns are quite symmetric. In the case of this is the velocity field. You can see that the right and left flows cancel each other. So this particle does not move at all with the electric field. But in the case of the hyperbolic hedgehog, you can see that the symmetry of the flows is completely broken. So this particle starts moving in the direction of the hedgehog. So this is fine, but now the question is why the particle moves in this particular direction. Can we reverse the direction of this motion? And so for that we are doing some, the images here are kind of shifted, but the main idea is to superimpose the flows with the polarized image of the particle, and at the same time superimpose the flows with the projection of the molecules or the director field around the particle. So we can see that the flows coming from the left are mainly parallel to the director, and the flows coming from the right are meeting the director in a perpendicular fashion. So if we take the ratio, we can see that mu parallel is larger than mu perpendicular. That means that the ions in this direction move faster compared to this side of the sphere, and so this breaks the balance of the flows, and that's why the particle moves in this particular direction. So if this sketch is true, then there must be a ratio of mu parallel and mu perpendicular that can reverse the flow. That is, when mu perpendicular is larger than mu parallel. So for that, we have the perfect candidate. We use this material because it changes the ratio of mobilities as a function of temperature. In this case, the transition occurs around 55 degrees. Above that, mu parallel is larger than mu perpendicular, and below that, mu parallel is less than mu perpendicular. And so the motion of the particle is corresponds to the transition of these ratios, in the sense that we can reverse the directionality of the particles as a function of the ratio of mobilities. So if the balance is controlled by the ratio of mobilities, then we can think that there is another ways to modify the trajectories of the ions around the particles, which in principle should modify the integral of mobilities along the path. So in this case, we are using a non-zero delta epsilon. So when we apply electric field, what we are doing is just modifying the orientation of the liquid crystal around the particle. And we can see that in the case of high frequency, for example, we have the same case as before. But as I decrease the frequency, the flows can be completely balanced, so the particle doesn't move at all. And in the case of low frequencies, we can reverse completely the direction of the flows. And the pattern shows precisely this. So now we want to compare the nematic case with the isotropic particles or isotropic fluids. But of course, in the isotropic case, we don't have defects. So we have to somehow simulate the symmetry that we have in the nematic case. For example, for the quadrupolar type of configuration in the nematic, we have only gold sphere, so this is completely symmetric. And we observe kind of the same quadrupolar pattern that we observe for the Saturn ring. And the flows, again, cancel each other, so this particle does not move. But if we break the symmetry with, for example, a Janus sphere is nothing else but a silica sphere in one hemisphere and a metal or some other material on the other hemisphere. So we are breaking the left-right symmetry in this case. And what we see is that the flows again break the symmetry. And these particles will move, for example, in this direction, and this particle will move in this direction. So it's very similar to the case of the nematic case. And finally, we want to explore how the salts affect the strength of these flows. We see something very unusual. Usually when you put salt in a aqueous solution and you perform experiments of electrophoresis, the velocity usually goes down immediately. But in our case, we have some room in the case that we have up to 10 millimolars before we reach saturation and the velocities start going down. So this is just an example of how the flows are modified because of the effects of the salt. So in this case, the image that is not presented here should be much better than in the previous two. So in summary, we have experimentally demonstrated that the motion of particles occurs because of the induced flows around the spheres, and we can control the directionality of the flows depending on the ratio of mobilities in the liquid crystal, and the induced flows or the breaking of symmetries is comparable to the case of isotropic as long as we have the same symmetries in the system. I think that's it. Thank you.
Questions? Those green pictures of the flow, those are actual experimental data?
Here. Doesn't move. You mean this?
Yeah, those middle images?
Those are pure experimental. I don't do simulations at all.
Okay, well, how did you get those images?
This image here, you take a series of images, like a lot of images. In this case, I am using 2,000 images, like consecutive images. And what I do is just to merge all of them in a single image. So you can see that for the first image, the seed will move just a little bit, but in the next image, it will also move a little bit. So when you superimpose these two, you get a small line, right? So the longer you take the frame, the video, and the more images you average, the more lines you will be able to see in your pattern. And this is again, this is not simulation, this is just the sort of correlation functions of these traces over time. So this is the velocity fields that correspond to this sequence of images.
So you're attributing the anomalous motion, if you like, of this particle to a symmetry breaking in the ionic flow, is that right?
Yes, in the ionic mobilities.
So is there some theory for that, or why?
There is no theory at all. No. Yeah.
Right, thank you very much.